remember this. Okay, I'm not sure whether this is the correct way to represent it, but think of it this way. This part is F, right? This part is G. So anything in between is FG. So I don't explain anymore. But so in order for F to reach G, you need to add FG. So the X itself is actually like a loading bar. So let's say how close it is to G. So I don't know whether that makes sense or not. But yeah. So F, if you add the whole value of FG, it will become G. So if your X is 90%, let's say, so it means that it has finished loading the FG by 90%. So here it's just simply X over here. That's how I don't know whether that's more confusing or not. So always remember this one. So F by FG is G. That's the simple idea. So that X is simply just how close it is to B. That's all. Alright, so we look at how we solve this. Now, the first slide, I will just go through quickly because this is exactly the same as yesterday's notes. So state 1, use saturated liquid state, you get H1, P1. State 2, we know the pressure, so you can use the work pumping equation to find the work pumping value. And then from there, you get H2 value. And then state 3, we have all the values. We have 50 megapascal, 600 degrees Celsius. You can get H3 and S3. Okay, so this slide, nothing special, exactly the same as yesterday, because it's the exact same states. Okay, then we move on to the next one. Now, so just now when I was showing you how to solve this, we actually approach it right away from state 6, right? So actually, even if you are not sure, like let's say because you didn't do this as much as me, so like me, when I look at it, I know you can start from state 6. If you don't know, you can actually still start from state 4, but you just write, basically again, it's the same thing, you just write down everything. So like state 4, if you write halfway, you realize, okay, I don't have enough information. You just leave the whatever that you wrote there first, then you move on to the next state. So you reach the state where you can see that you have enough information, then you start from there. So like in this case, I know state 6, so I started from state 6. So state 6 was what we said just now. We know what is T6, which is 10 kilopascal. X6, we set it at 0.896, that's the minimum value that we want. Then from there, you can calculate X6, you can calculate H6. Okay, so from here, we can move on to state 5. So from state 5, we know that T5 is 600 degrees Celsius, S5 is S6, and the answer that you get should be approximately 4 megapascal from the superheated steam table or vapor table. And then from there, you can also get the H5 value. Then after that, okay, so you can also add a bit of explanation for the answer. So the steam should be reheated at a pressure of 4 megapascal or lower to prevent a moisture content above 10.4%. Okay, so here we say that this 4 megapascal is the maximum. And someone tell me why.
If you go above the 4 megapascal, then your moisture content will be SC.
Why? Why will be lesser? Moisture content.
Will be more than 10.4%.
Why?
Because just now we used the 10.4 do the calculation. Because higher temperature, the temperature will be
using temperature is correct, but you miss out one thing. You should say that because we are maintaining the same temperature. So graph also, it will be a bit more obvious also. So let's say, okay, I cannot zoom and draw. So let's say, because we are maintaining the same temperature level, if higher pressure, it will mean that it will go from here. So when it reaches the same temperature, then yes, you get more moisture content. So if lower, then you have no issue because to reach the same temperature, it needs to go further to the right. So this is a rough idea. That's why this pressure is the maximum pressure because you are maintaining that same temperature level based on this question. So again, ultimately these are all design issues. You are choosing all these values based on what you want. Okay, so like in this case, what we want is the 89.6% quality. We also want T5 to be a fixed value. That is why 4 megapascal is the maximum value. Okay, so now we are done with state 6, we are done with state 5. We jump back to state 4. So if initially, so let's say now, if you started from state 4 instead of state 6, most likely what you reach, the conclusion that you will reach is this. So you know P4, you don't know P4, sorry. P4 is a question mark. You only know that S4 is S3, that's all. So you don't know anything, you jump, so you go to state 5. So state 5, once again you know that you don't know what is T5, because that's what you are supposed to find. But you know T5 600, you know this is this. So again, we still don't have enough information because S5 we don't have a value. Then you reach state 6. So most likely if you go from 4, 5, 6, then that will be the process that you go through. Okay, so again, there's no fixed order for this, like how you approach this. Again, ultimately it is your experience. You look at it, then you know which one is which. So that's why I like to try them out first. Okay, so now we have reached a conclusion that maximum pressure is 4 megapascal. So then P4 is P5, which means P4 is 4 megapascal. And then we know that S4 is equal to S3. So S3, we found it from the previous slide. Then based on this, you can go to the... Okay, now, so this one is something that is not fixed. Maybe here the diagram is very obvious, so let me erase this one first. Okay, so in this diagram, it is very obvious this is a superheated state. Now, in your, let's say even in the tutorial, you will see similar case where state 4 can actually be saturated vapor, it can also be mixture. There is no fixed answer to this thing. Because like I said, 4 megapascal is a low, is the minimum, right? Maybe the actual case is like 2 megapascal, let's say, then maybe the line will go on lower, then you will enter the saturation line. So there is no fixed answer here. Which means whenever you approach state 4, you should still, actually same as state 6. State 6 is also not a fixed state. So for this loop, you should always check again, see which state it is, so that you know which state you are using. It can be a mixture, it can be saturated vapor, it can be superheated vapor. So these three are possibilities. So here, this is still superheated vapor, and I believe you will need interpolation because T4 is 375.5 degrees Celsius. I think this one, the question just find for fun. I don't think it asks for temperature, you really need the temperature. You really need the H in this case. Because we found T4, T5, ultimately what we want is the thermal efficiency. Okay, so we move on. So since now that we have all the enthalpy value, then we can calculate the thermal efficiency. You can calculate Q in by using H3 minus H2, H5 minus H4, so don't forget the reheat part. And then, so in order to save ourselves some trouble, we use Q out instead because Q out is only one calculation. Technically speaking, you can still use work out, but then if you use work out, don't forget that you have two turbines, not just one. So easier to make mistake there. Let's do this way. So, but then two equation is the same. Then now thermal efficiency 1 minus Q out over Q in, then you can get the new thermal efficiency which is 45%. So now we compare this back with the final example that we did yesterday. So the previous example, our moisture content was 19.6. So now of course we purposely designed it to 10.4, so it's 10.4. But efficiency has also been increased by 2% because by just the reheat part. So you can see that if reheat, to be fair, the main point is still not the thermal efficiency because the increase is not as high as before. Because just now even our note says 4% maybe, but here our calculation shows that it's just 2%, and this is the ideal case. If you calculate the actual case, probably it's even lower. Probably now again, we don't know until we actually calculate that. But moisture content wise, yes, definitely has been improved. So that is actually more of the main point because you don't want your turbine to corrode that fast. So you want that much more moisture content there. Okay, so this is the end of example for reheat ranking cycle. So everyone can everyone understand this? Any issue?